Chemical properties of group 2, that is alkaline earth elements. Alkaline earth metals are less reactive than alkali metals. So when it comes to the alkaline earth metals, they are less reactive than the alkali metals. The reactivity of these elements increases on going down the group. So as you go down the group, the reactivity increases. Now reactivity towards acids and water. Beryllium and magnesium are kinetically inert to the oxygen and water because why they are kinetically inert? Because both beryllium and magnesium develop a layer of oxide on their surface. This layer of oxide actually prevent the matter underneath to react with the air and water, and thus the metal underneath become inert kinetically, and that is why they are kinetically inert to the um, air and water. Powdered beryllium and magnesium burns in air and form oxides and nitrides like MgO and Mg3 and 2 or BO and B2 and 3. Magnesium is more reactive and burns with white dazzling flame and produce magnesium oxide and magnesium nitride. Calcium, barium and radium reacts with air and water to give oxide, nitride and hydroxides. See, these hydroxides are generally produced by the reaction of the oxides with moisture. Going down the group, reactivity towards water increases and the reaction becomes more and more vigorous. So if you go down the group after calcium, strontium and barium, they react vigorously with water. Reactivity towards halogen. All the alkaline earth metals combine with halogen at elevated temperature forming their halides. See, they have generally, they form M plus 2 ion. So with one M X2 combined, X is fluorine, chlorine, bromine, iodine, which generally form the negative 1 ion. And that is why the kind of halides they form are MX2 type. Preparation of BeF2. Now see, how do we have seen that we can prepare the various other halides, but the beryllium fluoride and beryllium chloride are not prepared in the same way. So let us see how we can prepare beryllium fluoride BeF2. So BeF2 is prepared by the decomposition of ammonium beryllium fluoride. So see NH4 twice BeF4, when it is heated it gives us the 2NH4F and BeF2. So this is how, my dear students, we get BeF2 prepared. Now let us see how we can prepare the BeCl2. So BeCl2 is prepared by the reaction of beryllium oxide, carbon and chlorine, and thus we get BeCl2 and carbon monoxide at 600 to 800 Kelvin temperature. All the elements of group 2 except beryllium combine with hydrogen to form hydride MH2 on heating. So my dear students, all the elements of group 2 except beryllium combine with hydrogen to form the hydride of MH2 type. You can see that metal may be magnesium, calcium, strontium and barium. These metals, they react with the hydrogen to produce MH2. Let us understand it with the example. For example, calcium metal when reacts with hydrogen, it produces calcium hydride CaH2. Then how we can prepare BeH2? So BeH2, however, can be prepared by the reaction of BeCl3 with LiAlH4. This LiAlH4 is known as the lithium aluminum hydride, my dear students. So BeCl2, when it reacts with the AlCl4, it gives 2BH2, LiCl and AlCl3. Please remember these reactions. It is the reaction that is frequently asked into the various exams. So preparation of BeH2, preparation of BeCl2 and preparation of BeF2, they are the questions that are frequently asked into the various exams here and there. Let us study about the reactivity towards acids. So these alkaline earth metals reacts with the acids, liberating hydrogen. This is the common characteristics of the metals. Metals, when they react with acid, they produce hydrogen gas M plus 2 HCl, that gives MCl2 plus H2. Here M represents all the elements like beryllium, magnesium, calcium, strontium and barium. All these metals can produce hydrogen gas when they react with the acid. Now, my dear students, we want to study about the reducing nature. While studying all these metals, we came to know that reducing nature actually depends upon the electrode potential value, E0 value, and E0 value actually depends upon the hydration enthalpy, or it depends upon the charge is to size ratio, my dear students. Charge is to size ratio. This is the type of reaction where they truly depends upon. So, like alkali metals, alkaline earth metals are strongly reducing because metals are generally reducing in natures, and they are more metallic, and that is why compared to the D, F, and P block of metals, these metals are strong reducing agents. This is indicated by the large negative value of their electrode potential. This E0 value is large negative, and it shows that they are very good reducing agent. However, their reducing power is less than those of the corresponding alkaline earth metals. So in the same group, if we compare the reducing power, then the reducing power of alkaline earth metal is less than the uh, alkali metals. So the reducing power of alkaline earth metal is less than the reducing power of alkali metals, or you can say group 1 metals. So group 2 metals have a lesser reducing power or lesser reducing character as compared to the group 1 metals. However, it is reducing nature is due to the large hydration energy associated with the small size of Be plus 2 ion and relatively large value of atomization enthalpy of metal. So the highest value is there with the beryllium Be plus 2, and Be plus 2 is the most reducing in nature, and this reducing in nature is majorly due to the small size of Be plus 2 and charge is to size ratio, or you can say the charge density, and at the same time the large value of the energy of the atomization that can be easily overcome by the uh, value which is known as the hydration enthalpy. Now, my dear students, we want to study about the solutions in liquid ammonia. So let us study about the solutions in liquid ammonia. Like alkali metals, the alkaline earth metals dissolves in liquid ammonia to give deep blue black color. See, the alkali metals were just giving the deep blue color, but here we get deep blue black color. Forming the ammoniated ions and the ammoniated electron, you can see that M plus X plus Y NH3 that gives MNH3 MNH3X plus 2 into ENH3Y. This is what it is known as the ammoniated electron, and this is what it is known as the ammoniated ions. From these solutions, the ammoniates MNH3 6 plus 2. Please remember that from here we get the MNH3 6 plus 2 kind of MNH3 6 plus 2 kind of complexes can be recovered from this solution. Please remember. Now, please, you even need to note that beryllium Be cannot make NH3 6 plus 2 type of ions because its covalence is limited up to 4. So for beryllium, we cannot have these ammoniates, but for the other elements, we can easily find these ammoniates from this, or we can easily recover these ammoniates from this ammonia solution. Now we need to study the various uses of these elements. Beryllium is used in the manufacture of alloy. So copper beryllium alloy, first we will study the various alloys. So copper beryllium alloy are used in the preparation of high strength springs, especially the springs which are used into railways and trucks and buses and tractors and at various places. Same way, metallic beryllium is used for making the windows of X-ray tubes. You know, when we go to doctors, they suggest us to go for X-rays. These X-rays, when they are taken, the X-ray window tubes are made from the uh, beryllium metal. Magnesium forms alloys with the aluminium, zinc, manganese, and tin. So magnesium also forms the various alloys, and these various alloys are useful in a very different manners. Let us see how they are useful. Magnesium aluminium alloy being light used in the aircraft construction. So magnesium aluminum alloy is used into the aircraft constructions. Magnesium powder or magnesium ribbon is used into the flash powder, bulbs, incendiary bulbs and signals. So these are the various uses of the magnesium powder. These incendiary bombs are the bombs that we generally use during the Diwali, or we can call them the crackers. uh, a suspension of magnesium hydroxide. A suspension of magnesium hydroxide in water is used as an antacid, which is known as the milk of magnesia. So this milk of magnesia being basic in nature, it reduces the acidity that has been produced into the stomach, and that is why this milk of magnesia is used as an antacid. Magnesium carbonate is ingredient in the toothpaste. My dear students, the various toothpaste that we use, this magnesium carbonate is used as an ingredient into the toothpaste. Uh, Calcium is used in the extraction of metal. For the metal which are difficult to reduce with the carbon, they are reduced with calcium. So those metals which are difficult to be reduced with the carbon, these metals are being reduced with the calcium. For example, during the process of lead refining, in the steel purification, or in the extraction of uranium, thorium and zirconium, this calcium is used as a reducing agent. So please remember this, my dear students, that calcium can also be used as a reducing agent. When the carbon fails to reduce the metals, calcium is used as a reducing agent. Let us look at the other uses. Calcium and barium reacts with oxygen and nitrogen at elevated temperatures. So they have capacity to react with the oxygen as well as nitrogen at elevated temperature, means at high temperature. So they are used to create vacuum into the vacuum tubes. So when there is a vacuum tube, these barium and calcium metals are placed inside and they are allowed to burn. So all the oxygen and nitrogen present inside the vacuum tube, it will burn, and that is how the vacuum can be created into the vacuum tubes. Radium, which is a radioactive element, radium salts are used into the radiotherapy, especially for the treatment of the cancers. So my dear students, these were the various uses of our metals that we have been studying. Now we want to study the general characteristics of compounds of the alkaline earth metals. So let us study about the general characteristics of the metals of the alkaline earth metals. The di-positive oxidation state, that is M plus 2, is the predominant valence of group 2 elements. So the di-positive oxidation state M plus 2 is the major oxidation state that we can find for the alkaline earth metals. The alkaline earth metals from compounds form, actually not from, it's form form compound which are predominantly ionic but less ionic than the corresponding compounds of alkali metals. So the compounds of alkaline earth metals are comparatively less ionic, but they are generally ionic in nature. This is due to the increased nuclear charge and smaller size. So as we move left to right, my dear students, the charge increases and size decreases. So the charge density or charge is to size ratio for alkaline earth metal is little more, and that is why they develop a little covalent character as compared to the alkali metals, and that is why they are less ionic, but they are ionic in nature. The oxides and other compounds of beryllium and magnesium are mostly or more covalent. So, as having the very small size, the compounds of magnesium, especially the oxides and hydroxides of magnesium and beryllium, they are covalent in nature, and they are covalent than those formed by the heavier and large size members like calcium, strontium, and barium. So oxides and hydroxides are more covalent as compared to the oxides of calcium, strontium, and barium. The general characteristics of some of the compounds of alkaline earth metals are now we'll study about them. So first let us study about the oxides and hydrides, my dear students. The alkaline earth metal burn in oxygen to form the monoxide, which is MO, which except BeO have rock salt structures. So except BeO, all the other MO have the rock salt structures. They have wonderfully well arranged particles. The BeO is essentially covalent in nature. So this BeO, which is essentially covalent in nature, the enthalpy of formation of these oxides are quite high, and consequently they are very stable to heats. So the enthalpy of formation of these oxides are very high, and they are very stable to heat. BeO is amphoteric in nature, so BeO is it react with both acid as well as base, and that is why it is amphoteric in nature, while oxides of other elements are ionic in nature. So these oxides of other elements, they are ionic in nature. All the oxides of group 2 elements except BeO are basic in nature. So except BeO, all the other oxides of the group 2 elements are basic in nature. Only BeO is amphoteric in nature. BeOH twice, that is beryllium hydroxide, is also amphoteric in nature. Elements forms oxides MO. So these elements, they form the oxide which is MO type, where they one atom or one ion of M plus 2 combines with one ion of O minus 2, which are ionic, so water soluble, and forms the hydrides when dissolved in water. So this MO type of oxides, when they react with water, they produce MOH twice type of hydroxides, and these hydroxides are also water soluble. Going down the group, from magnesium to calcium to strontium to barium, the solubility, the thermal stability, and the basic character of these oxides increases down the group. So as you go down the group, the solubility of this hydroxide increases, the thermal stability of this hydroxide increases, and the basic character of the hydroxide increases. So we can say that compared to CaOH twice, BaOH twice is more soluble in water, is more thermally stable, and is more basic in nature. That is what we can easily understand. Hydroxides of group 2 elements, that is alkaline earth metals, are less basic and less stable than the hydroxides of group 1, which are alkali metal elements. So hydroxides of group 2 elements, which are known as the alkaline earth metals, are less basic and less stable than the hydroxide of group 1 element. So when we compare this hydroxide with group 1 hydroxide, they are less basic in nature. Now my dear students, we want to study about the beryllium hydroxide. So let us study about the beryllium hydroxide. Beryllium hydroxide is produced as a byproduct in the extraction of beryllium from its ore beryl or bertrandite. So this beryllium oxide is produced by as a this beryllium hydroxide is produced as a byproduct during the extraction of beryllium from the from the ore beryl or bertrandite. Beryllium oxide is insoluble in water. Please remember, my dear students, this is even an important point, that beryllium oxide is insoluble in water due to the high lattice enthalpy of BeO, and hydrogen enthalpy is not enough to overcome this lattice enthalpy. Thus, BeO is insoluble in water. So you can think that the lattice enthalpy of BeO is very high, because Be plus 2 even contain the very high hydrogen enthalpy due to the very small size and high charge density. But still the lattice enthalpy is so high that the hydrogen enthalpy does not overcome it, and beryllium oxide is water insoluble, and that is why beryllium hydroxide, BeOH twice, cannot be prepared by dissolving BeO into water, and it is just obtained as a byproduct during the extraction of beryllium from the ore beryl. Beryllium hydroxide is amphoteric in nature, so it reacts with both acid as well as base, and it reacts with both acid as well as base. So you can see the reactions of beryllium hydroxide with 2OH minus, which is a base, or you can say it reacts with the alkali to produce BaOH4 minus 2 ions, and this BaOH twice, it reacts with the acid, that is HCl. We get BeH2O4Cl2, that is hydrated beryllium chloride, my dear students. The same reaction we can even represent as BOS twice HCl into 2H2, which is also known as BeCl2 into 4H2O. So this is how we represent the beryllium chloride in two different manners. Now, my dear students, we want to study about the halides of these elements. Except for the beryllium halides, all the other halides of alkaline metals are ionic in nature. So we easily understand that they are ionic in nature. Beryllium halides are essentially covalent and soluble in organic solvents. This is what it is due to the high charge density of beryllium that causes the covalent character, and that is why they are soluble, or beryllium halides are soluble in organic solvents. Beryllium chlorides has a chain structure in the solid state. This is even an important point, my dear students. In the solid state, this beryllium chloride actually has a chain structure. You can see the chain structure of beryllium chloride, and it forms the polymer. But when it is heated and at high temperature, when it is turned into the vapor state, uh, below 1200 Kelvin, this beryllium exists as a chloro-bridge dimer. You can see these two bridge bonds, which are shown with the dotted lines. And this is how below 1200 Kelvin, this beryllium behaves as a beryllium bridge dimer. But above 1200 Kelvin, my dear students, at high temperature of above 1200 Kelvin, this beryllium exists as a linear BeCl2 monomer, and the bond angle is 180, and that is why we call it linear. In the vapor state, BeCl2 tends to form a chloro-beige dimer. Chloro-beige bond is represented with the dotted line, my dear students, we have seen in the figure. Chloro-bridge dimer dissociate into linear monomer at high temperature of the order 1200 Kelvin. Linear BeCl2 has a bond angle 180 degree. The tendency to form hydrated halides decreases down the group. For example, you can see that MgCl2 can form 8 H2O, CaCl2 can maximum have the 6 water of molecule, SrCl2 6 H2O, but BaCl2 only 2 H2O. So as you go down the group, the hydration uh, or the tendency to hydrate is decreasing. When hydrated halides of calcium, strontium, and barium are heated, they are dehydrated. You can see that CaCl2, when it is heated, it gives CaCl2 and 6H2O. So the water of crystallization is being removed by heating. But in case of the beryllium, it is not so. Hydrates of beryllium and magnesium halides, that is MgCl2 into 6H2O, suffers the hydrolysis reaction. So my dear students, you can see that MgCl2 into 6H2O, when it is heated, it gives MgOHCl plus HCl plus 5H2O. Again on heating, this MgOHCl and HCl turns out into MgO and 2HCl. And finally we get, so when MgCl2 into 6H2O is heated, we get MgO, 2HCl and 5H2O. This is how this MgCl2 undergoes the process of hydrolysis, and we get magnesium oxide and two hydrochloric acid molecules. Fluorides of alkaline earth metals are less soluble than the chlorides of alkaline earth metals. My dear students, the fluorides are very small and they have very high electronegativity. So they form the compounds with the alkaline earth metals which have very high lattice enthalpy, and that is why they are less soluble in water as compared to the chlorides. Chloride being bigger, the lattice enthalpy is comparatively less than the fluorides. Because group 2 metal fluorides have high lattice enthalpy, and thus they are not so soluble as the chlorides are soluble. Now, my dear students, here we want to study about the salts of oxoacids. The alkaline earth metal also form the salts of oxoacids, my dear students. The carbonates of alkaline earth metals are insoluble in water and can be prepared by adding sodium or ammonium carbonate solution to the solution of soluble salts. So, my dear students, the carbonates and carbonates of these group 2 elements are water insoluble, and they can be prepared by adding the sodium carbonate to the halides of any of the metal. Here we have taken the example CaCl2. When it reacts with Na2CO3, it gives us CaCO3 and twice NaCl. Same way, my dear students, solubility of carbonates of group 2 metals decreases and thermal stability increases as we go down the group. So as we go down the group, the solubility decreases and thermal stability increases. Carbonate ion is a bigger ion, so big ions like calcium, strontium and barium can accommodate them well, and that is what it causes the less distortion due to the decreased the charge is to size ratio, and thus they have the bigger group 2 metal carbonate, and thus these metal carbonate of group 2 elements have higher lattice enthalpy. As they have high lattice enthalpy going down the group, the solubility decreases but the thermal stability increases. So as we go down the group, carbonates are bigger ion, and that is why the bigger calcium, strontium and barium ions, they can accommodate them very well, and that is why going down the group, the stability, thermal stability increases but the solubility in water decreases. Uh, Thermally, MgCO3 is less stable than CaCO3. Please remember that MgCO3 is less stable than CaCO3. Same way we can see that MgCO3 is less stable than CaCO3, CaCO3 is less stable than SrCO3, and SrCO3 is less stable than BaCO3. This is how, my dear students, we study about the various carbonates and their stabilities. Uh, BeCO3 does not exist in the solid or does not get stabilized until kept into the atmosphere of CO2. So beryllium carbonate is not possible in the solid state because it is very unstable and decomposes at room temperature to produce beryllium oxide and carbon dioxide. At room temperature, BaCO3 is unstable, so it decomposes easily, and so to stabilize it should be kept into the atmosphere of carbon dioxide. So sometime if you are asked that why beryllium carbonate is kept into the carbon dioxide atmosphere, you can answer these questions. Now, my dear students, we want to study about the sulfates of group 2 elements. The sulfates of alkaline earth metals are all white solids and stable at heat. BeSO4 and MgSO4 are readily soluble in water. The solubility in water decreases as we go from calcium sulfate to barium sulfate. So these sulfates are white substances. They are all sulfates are water soluble, and going down the group, the solubility decreases because of the bigger ions like calcium, strontium, and barium. They accommodate the big SO4 minus ion, and that is why the lattice enthalpy increases, and that is what it causes the decrease into the solubility. But at the same time, the thermal stability increases as we go down the group. BeSO4 and MgSO4 are readily soluble in water because Be plus 2 and Mg plus 2 are small in size. So Be plus 2 and Mg plus 2, which are small in size, so they have high charge is to size ratio, which cause the high hydration enthalpy, and this hydration enthalpy overcomes the higher lattice enthalpy, and thus the uh, sulfates of beryllium and magnesium are water soluble. Thus, BeSO4 and MgSO4 readily soluble in water. MCl2, any kind of halides, when it reacts with the H2SO4, these sulfates are produced. So these sulfates of group 2 elements are produced by the reactions of the halides of the group 2 metal with the sulfuric acid H2SO4. Now, my dear students, we want to study about the nitrates. So nitrates of group 2 metals are prepared or made by the dissolution of the carbonates into the nitric acid, MCO3 into 2HNO3, that gives MCO3 twice into H2O into CO2, that MNO3, I'm sorry, we get MNO3 twice into H2O into CO3. This is what we can easily understand from the example CaCO3. When it reacts with the nitric acid, it gives CaNO3 twice plus H2O plus CO2. Magnesium nitrate crystallizes with 6 molecules of water, MgNO3 into 6H2, whereas barium nitrate crystallizes as an hydrogen anhydrous salt. So BaNO3 is anhydrous. It does not has any sorry water of crystallization. It shows that decreasing tendency in group 2, that as we metal nitrates for hydrate formation and solubility in water. So my dear students, as we go down the group, the hydrate formation and solubility in water decreases for the nitrates of group 2 elements. Um decreasing hydration enthalpy. All the all the nitrates of group 2 decompose to give the oxides, nitrogen dioxide and O2 gas. You can see the common or general reactions. If you have 2MnO3 twice, that gives us 2MO plus 4NO2 plus CO2, and all these magnesium, beryllium, calcium, strontium and barium nitrates give the same kind of reactions, my dear students. Now we have a question. Why solubility of alkaline earth metal hydrate, hydroxide in water increases down the group? The solubility of hydroxide increases the down the group. Among the alkaline earth metals, hydroxide, the anion being common, uh, the cationic radius will influence the lattice enthalpy with increasing ion size, and thus the solubility increases as we go down the group. So, my dear students, as we go down the group, the uh, lattice enthalpy actually decreases, and as the lattice enthalpy decreases, as the size increases, these hydroxides going down the group become more and more soluble in water. Why does the solubility of alkaline earth metal carbonates and sulfate in water decreases down the group? So carbonates and sulfates are generally bigger ions, and that is why going down the group, the size of an ion being much larger than the cation going down the group, size of cation increases and charge is to size ratio decreases. Thus, Thus, hydration enthalpy decreases due to the decreased charge density ratio, so solubility decreases for the carbonates and sulfonates of the group 2 metals as we go down the group. Please remember, my dear students, that hydroxide ions are comparatively smaller than the sulfates and carbonates ion, and that is why going down the group, the solubility of hydroxide increases while the solubility of sulfates and carbonates of group 2 element decreases down the group. Now, my dear students, we want to study the anomalous behavior of beryllium. Beryllium being the first element belonging to the group 2, it shows the anomalous behavior. Beryllium, the first member of the group 2 metals, shows the anomalous behavior as compared to the magnesium and rest of the members. Further, it shows the diagonal relationship with the aluminium. Let us see, the beryllium has exceptionally small size, both the atomic size and ionic size, and because of this small size is because of the high ionization enthalpy, and because of the high ionization enthalpy and small size, beryllium has got charge size ratio very high or very high charge density, and due to this, what happens, the compounds of beryllium are largely covalent in nature and get easily hydrolyzed. So compounds of beryllium are generally covalent in nature comparatively to the other, and they can be easily hydrolyzed. Please remember, they undergo the hydrolysis. They are not hydrated, please mind well. They are hydrolyzed, not hydrated. Beryllium does not have D shell in its valence shell, so beryllium could not make more than 4 bonds at a time, and that is why the covalence of beryllium is limited up to 4, and that is why but the covalency of the other elements of this group eh, can be extended up to 6 due to the availability of the vacant d orbitals. The oxides and hydroxides of beryllium are amphoteric in nature, while the oxides and hydroxides of the other elements of group 2 are basic in nature. Now, my dear students, we want to understand the diagonal relationship between the beryllium and aluminium. The ionic radius of B plus 2 and charge is is to radius ratio of both aluminum and beryllium are resembles with each other, and that is why both the aluminum and beryllium show similarity in their characteristics. Let us see what are the various similarities that we can see. Number one, like aluminum, beryllium does not attack by acid because of the presence of the oxide layer on it. Second one, beryllium hydroxide dissolves in excess of alkali to give berylate ions. Same way aluminum also forms the aluminate ion AlOH4 minus. So BaOH4 minus and BaOH4 minus 2 and AlOH4 minus 1 are very similar to each other. Same way, the chlorides of both beryllium and aluminum have Cl minus breach So this bridge dimer or bridge Cl minus bridge is possible for both the aluminium chloride and beryllium chloride in the vapor phase, my dear students. And both beryllium chloride and aluminum chloride are electron deficient. They do not have complete octet, and that is why they behave as a Lewis acid. And that is why this beryllium chloride BeCl2 and AlCl3 can be used into the Friedel-Crafts reaction, my dear students.